Hello, everyone, and welcome to this webinar from SuperAnnotate. I'm really excited to see so many of you joining us today. We are going to talk about OCR, a bit about what it is and why we should care about it. And the layout of this today is going to be, we're going to start having a bit of a dive down into the history of OCR, kind of the origins, where it comes from, and how it has developed over time. After that, I would love to dive into kind of how OCR works today, the different components of it, and how those systems are built up. Following on that, I'm going to move into a bit of applications of OCR, kind of the why we should care part. What does it do for us? And what are the future fields where it is opening up a lot of new, both knowledge and applications for us. And of course, focus a bit also on what makes OCR hard and what can we do to make OCR projects we're taking on easier. So without further ado, let's jump into this. So I'm starting this in the 1960s in this slide, but to some extent, you can say that OCR extends well before that. There are patents and records of machines as early as the early 20th century, even late 19th century, that was used to help blind people read. We had machines that could optically scan pages and transform those patterns into sound that you could use to read if you were very skilled at hearing these sound patterns, at least. It's something that took quite a lot of training. But for the purposes of more modern OCR, we're going to start this story in the 1960s. And that is when OCR-A and OCR-B was invented. So specialized fonts designed specifically for machines to be able to easily read and parse it using kind of key points on these letters. And that's what they were created to be used to aid with scanning materials and things like that. And actually, these fonts are still used on passports today. If you see the little machine readable section, usually far down on the first page. We move on a bit into 1975. Then Kurzweil Computer Company created a product that was the first one capable of reading more than just one of these specialized fonts, but still a very cumbersome setup that you usually would have in a specialized processing facility. So it's not something everyone was using. Moving on to the 1980s, 20 years ahead, this is when OCR actually started to get a lot of use. It became widely popular in retail, and chains such as Kmart and other large grocery chains started to use these various price tags to be able to easily process that. It was something that went on until 1987, where instead barcodes was adopted as the standard for retail uses, as it is still today. In 1983, as we touched a little bit on briefly, I started to use OCR on passports using these fonts for the first machine readable passports to be able to scan to get a lot of information out of. Further ahead in time, but still in the 80s, but something that is early enough to maybe surprise a few is that in 1989, we had the first convolutional neural network. It was invented at Bell Labs in New Jersey and used to read postal codes on letters. And this is kind of the foundation of both what you can say kind of modern day machine learning, but definitely modern day OCR. It's quite a big gap until the next big event here. But in 2002, Google started what they call Project Ocean, an initiative to scan and digitalize books en masse to make them both accessible on the internet through Google Books, searchable, and to make that information available to more people. Again, a step forward, and now into 2005, we have something called Tesseract, and that is an open source optical character recognition tool. And originally this was developed at HP in the 80s, but the reason to why it is here in 2005 is that is when this tool was released open source. This is when OCR tools became something that was available to the larger masses of developers to integrate into their software and services. Google kind of took the software under its wings and continued to develop this project for several years. In 2013, and this is kind of where my machine learning journey started. It's a very interesting data set. The MNIST data set, or MNIST, I guess you say it, a data set that is very commonly used for people getting started in machine learning to train their first convolutional neural networks on, but also as kind of a benchmark of optical character recognition of handwriting. That's still a hard task. So here we collected a large number of handwritten digits, different shapes, 0 to 9, but a massive data set that is, as mentioned, still used in a lot of benchmarking. We jump to the final point on this short journey through the history of OCR. It definitely does not stop at 2014, but this is when we had something called CNN. But OCR isn't just kind of transcribing text. In many cases, it's also finding where that text is. And originally, this was used, created or found using algorithms with handcrafted features that would look at like edge detection and things like that. Started to change parts of this out. And in 2014, we had the first fully convolutional neural network that did finding of text in scene, in the wild, as you can say, for the first time. So that is a brief overview of kind of the story of OCR, how have we gotten quite close to where we are today. And what I mentioned briefly is that there are a few different steps to OCR. It can be broken down into what we call text detection, or finding where in a scene we have text of interest. It can be maybe in a document we want to find headlines and lines, but it can be finding where is the license plate on a car, or indeed texts on signs that are spread out on photos. And in addition to this, we also have what we call text recognition, actually parsing and understanding the identified text, taking it from pixels on an image and transforming it into letters or numbers on a computer that can be processed automatically. Now let's take a little dive into text detection and see what that is all about. It started out, as I mentioned, with handcrafted features, people painstakingly sitting and figuring out how can we write a computer program to identify text in a scene. You can discover edges, find different types of image transforms to identify things that look like letters. And this created a lot of unnecessary like example or proposal regions where it said there might be text, but it turned out it wasn't. Also prone to missing things. And not the least, very difficult to make, develop, and maintain. In came the kind of revolution of deep learning and neural networks. We could get rid of the handcrafted features and use data and targets or labels to automatically identify where we have these objects using the fully convolutional neural network. This one creates bounding boxes, but not all use cases a bounding box is what is necessary. There might be situations where we have maybe circular text and this type of package, or rotated, and that is things that ordinary bounding boxes just really can't capture. So something called differential binarization segmentation, an algorithm that came a bit later, expanded this. Instead of applying an object detection approach, applies more of a segmentation approach, attempting to find all the different parts or pixels of an image that contain text content and creates these sorts of masks to outline them. After finding the text in a scene, we need to parse it. And this is where we move on into kind of the text recognition stage. This was also historically done with this maybe OCR-A, OCR-B text, where we could look at predefined key points. But again, moving further ahead into time, we usually do this using convolutional neural networks to parse images, maybe detect information about specific characters, and then add on some type of recurrent neural network, what can be called a long short-term memory, or other algorithms to kind of take time steps or spatial steps to identify where we have different letters and how they come together to transcribe this into a sentence. But these have a bunch of problems. As you can see in the image here, the spacing between letters may be different, but these algorithms look at fixed time steps or fixed spatial steps. So in one case, it might transcribe a sentence perfectly, but in other cases, if you have further spatial steps in between, you might get the same digit, the same letter twice, or maybe not even once if they're very tight together. And in 2006, an algorithm called CTC was developed to handle this. It can take the output of an algorithm like this and convert it into words. And you now didn't have to have each specific time step or spatial step in your kind of loss function. You can instead just transcribe the entire word in your training data and then use that to train your algorithm. So a big step forward. But of course, it didn't stop there. Like have happened with many industries, transformers, these big foundational pre-trainable models have stepped in here as well. You might recognize them from ChatGPT, the biggest, most famous example where you have language models, but it also stepped into the image sphere. We're working with image annotation instead. And what some people figured out what to do was that you can take kind of the image part of a transformer that encodes images that have been pre-trained on large amounts of image data to understand and capture relationships within visual data. And you could combine this with one of the large language models, kind of the decoder that can take these encoding abstraction that a transformer creates and instead give you language back. They put these two together, pre-trained models, and were able to create an OCR tool. Using that, demanded some sort of transfer learning. This is something that you can use to transfer learn yourself on smaller data sets because it already has that high level understanding of what is text, what is language. It therefore requires much less data to generalize to new tasks. So that is a little bit about how OCR is set up today. Generally, even with a transformer, have two steps. You want to find a text in an image, and you want to transcribe the text in that image. But we also wanted to ask ourselves, kind of, why should we care about OCR? What can OCR do for us? So we're going to look a bit on OCR in the wild here, what it has been used for. And one use case, or many might have encountered it, is within parking. In many modern parking places, you no longer have to go and find a vending machine to put cash into it, get a little paper note out that you can put in the front of your car. Instead, in many cases, you enter your license plate number into an app and pay using your card or maybe Apple Pay in there. And then parking attendants or controllants can scan plates with their phone using OCR, both the kind of text recognition part to text detection part to figure out where in this image is the license plate, but also transcribing the content of the license plate. And this might seem simple, but it saves enormous amounts of hardware and time. You no longer have to put out these physical machines that need to have cabling and electricity. And you don't need to have as many people walking around checking tickets. It's all very simple. It saves both time and money. It's also very commonly used in tests. Starting out with the small where you just fill in a little circle, it's easy to detect, but also generalizing to where you write a letter or maybe some text and used to automatically grade exams. And something, for example, Cambridge English tests used to really speed up. It's a type of test that grades a non-native English speaker on English using university applications or immigration. And to be able to automatically grade those exams instead of having a person physically going through each and every one also, again, saves both enormous amounts of manpower, of cost, and also really cuts down the amount of time until someone can have the result that might be critical in will there be accepted to university or not. So something you really want quickly. These are two kind of simple applications, but one interesting kind of large scale application is also how you can use this within historical research. A bit that was touched on by the Project Ocean by Google, but it's growing and growing, and it's a really hot topic of research now. One of these is scanning and digitalizing historical archives, making them searchable, where a researcher maybe previously had to have a hypothesis, an idea, know which archives to go to find these physical documents that one might be in England, another in the US, and a third somewhere in Asia, which makes this very hard to understand. You can instead search the content of these documents in a database when they're transcribed. And it's also used, and a lot of research being done on kind of transcribing ancient languages. One language from Mesopotamia, a civilization thousands of years ago, that we have found a lot. They wrote in stone and clay tablets that we managed to find and recover a lot of. There are very few people in the world that knows how to read this language. And here, OCR and deep learning can be used to both identify kind of which tablets belong together, but also really speed up the amount of time it takes to transcribe them. As no longer do you need one knowledgeable scribe to read every single tablet. You can instead have them working on creating the training data for an algorithm to really speed this up. It unlocks massive amounts of historical information that otherwise simply wouldn't have been logistically possible to process and analyze. And this is, of course, also used in taxes and other types of governmental filings. And in some cases, it might be surprising how late this come. But paper filings that are used by a lot of agencies take a massive amount of time to handle. You need to read them. You can't use search, or you can't use process them programmatically. So digitalizing documents here can also save vast amounts of money, both here, but also, of course, for businesses or any other place where you're dealing with a lot of paperwork. But IRS, the American tax agency, started using more OCR methods actually this year. And so far, they've scanned more than 120,000 forms that they previously processed manually that can now be processed more automatically. And that cuts time to decision for people to get their agency decision. It also, of course, saves massive amounts of money as well. And these are just a few of a large amount of use cases. And if OCR can be this useful, why doesn't everyone use it and for everything? And there's a problem here, right? OCR is hard. Training OCR algorithms can be really tricky because there's a lot of different issues at hand. It can be the source material where you have problems. It can either be, of low quality, maybe have low resolution images, or in the case of stone tablets, they've been wear and tear over thousands of years. Or handwriting can be really tricky to understand if someone doesn't write clearly. It can also be kind of the accessibility of the data. If there's a very specialized use case, such as the ancient documents in archives or other type of data, it can be really hard to get your hands on. Maybe it's very sensitive, and that sort of data gathering can be really hard. It can also be a matter of very complex document layouts, or one document can be very different from the next, and the way you need to transcribe and process them might be very different, which also poses a problem in both how you create algorithms, but how you create your data sets as well. You also have kind of the problem with different writing. It can be both that you have a multitude of different languages. You want to build something that works not just for English, but for Mandarin, maybe Arabic, maybe a vast array of European, African, and South American languages as well. That both to generate this data set demands that you have knowledge of all these languages, or at least access to people that do. It also puts higher demands on your algorithms to be able to process and understand a vast amount of languages and not mix things up. But it can be varying types of scripts. I mean, you can have computer script, you can have handwriting that can be good, that can be bad, that can be very, very different from person to person. And also dealing with that especially in situations where, I mean, it might be hard for a human to read some handwriting as well. And teaching a machine how to do this poses challenges. There's some problems when it comes to handling ambiguity. Data isn't always clear and easy to label. It might be factors below image quality simply making it hard to read what it says, or different people interpreting things differently. So here, when both generating a data set for your algorithms, but of course also evaluating its predictions, consistency is key. You need to have a way for everyone that's involved in creating your data set to be really consistent with their decisions, to create a good, high quality ground truth data for a model that you're training, transfer learning. Because consequences of this kind of problem, it's just not limited to low quality images, but it can be huge. Imagine that you're developing an autonomous car, a self-driving system that drives down a road and needs to be able to scan speeding or the speed limit signs. And it might be tricky, it might be hard to see the difference between maybe a 30 and an 80. And the last thing you want is either your car speeding away on a low speed 30 stretch or come to a rapid halt when it mistakes the sign from 80 for 30, slams the brake and end up with someone running into you. So kind of small, easy mistakes and mishandling this sort of ambiguous situations can, in some cases, have massive implications, even for a task that is just recognizing writing. It's always important when you deal with ambiguity to kind of take into account what sort of situation this is going to be used in and what are the kind of stakes on hand. In addition to this, or maybe all of this taken together, make creating data sets when you're training OCR very labor intensive. We're talking about manual work that is needed initially. Once you have your trained OCR algorithm, amazing, it can do things automatically for you. And for some use cases, there are already good pre-trained tools you can either send your data to have it scanned, or Google Translate on your phone that you can hold up against a piece of text and automatically transcribe that for. But for more niche use cases, or where a high level of accuracy and quality is very important, you still have to fall back to that kind of manual work to create a data set, to manually transcribe data. And it might be huge amounts of data, documents, pictures of signs that need to be labeled as well. So both taken together have a very huge cost in terms of personnel. So the question then comes, how can you make this easy? Can, to a large extent, try to use automated tooling to lower the amount of work that needs to be done manually. Maybe the labeling tools that are out there, or kind of the OCR tools that are out there, aren't perfect, but it can create a good start to continue to work from. You can pre-label data, then go in and correct and adjust them. Also, things like training the annotators, and this especially falls back to both kind of tricky use cases when you have maybe a multitude of languages or ambiguous use cases that need to be handled in specific ways. If you have a team of annotators working and helping you creating a data set for your OCR applications, it can be very important to make sure that they all work in a consistent way. But even with training and instructions, mistakes happen. And this would kind of good quality control measures come in to play. It's about being able to catch mistakes and enforce consistency. But it's also necessary to kind of maybe work with a consensus approach. You can have the same annotators or maybe different OCR tools as well in the final application, transcribe and work with the same piece of data, and then calculate a sort of consensus score agreement between these to produce your final result. So for an overview of kind of the problems with OCR and what it is in history, this is something we've worked with a lot. And at SuperAnnotate, we're also working a lot with kind of helping companies create this sort of data. And there are a few approaches we've taken to address these problems that might be useful to some people. And I would love to showcase a little bit on how you can work with OCR, create OCR data within our platform. I'm gonna see if we can escape this one and show a toolbar. So we can move over to a new tab in SuperAnnotate. But this kind of what you're seeing in front of you now is one tool in which you can do OCR and kind of create your data sets, at least for OCR applications. You have a large amount of data in here and a few different tabs with settings and tools. I'm gonna cover very briefly shortly. But if we open up an item here, in this case, receipts. If you've been on business trips or on anything else like that, you might have used a diverse set of apps to automatically scan your receipt and get an expense report created for you. And this is about OCR. Like what we have in our platform is a tool to automate parts of the OCR process for you. You can select kind of a class here for metadata and use the magic box, the OCR tool in here. You can select this data like this, and we attempt to automatically transcribe and put this down into different categories. And what we have here is a green field for the name, the address lines, and the phone numbers looking quite correct. We have some different numbers here. And the important thing when it comes to kind of assisting you with data annotation needs and tools, it's that you can change these, right? We want to help in assisting creating a data set, but also be able to adjust afterwards. We can easily add a little tab or space there or change anything else that's necessary. May want to capture the information about the expense as well. Reset class for that. You can mark this items of text and get a view of both the subtotals, the tax, the total amount down here, and also again adjust if anything is incorrect. So this is one way in which automated tooling can help you create a data set faster. Quality control is also very important. If we jump out from there and showcase one type of example when you do quality control here, it's like either you can be inside one image, right? You can have a look, see does everything looks correct, or you can look as a transcripted record, so apply some sort of general rules if you know what it is you're transcribing, the kind of data, maybe something needs to add up. But also it's sort of set up where you can easily explore and have a look at much of the data at the same time can help. And here we can display different transcriptions and lines we have added to go in and easily catch mistakes, such as here we have an 8 instead of a 9. Open that up. Go in here, and if we right click, we can easily adjust that amount down here to 9. Correct. So this is one example of kind of how automated tooling that we have focused on building in our platform can help pushing data annotation for OCR forward faster by allowing you not to transcribe everything, but getting a lot of the assistance and then doing the final little touches yourself. And then be able to export and use this to kind of train or improve any OCR algorithms or projects that you're working on your end. Move back in here. So briefly, just want to mention kind of who we are who are holding this presentation today. After we zoom through this little slide once more, it's SuperAnnotate, or a company that really focuses on kind of data annotation. We're founded in 2018 by 2 brothers, and have since grown up until a team of kind of 150 plus machine learning enthusiasts working on both data and kind of tools to help push data and AI innovation forward, spread out of the US, the EU, UK, Armenia, and Bangladesh. And we offer both kind of a software platform with tools for annotation and to assist your ML pipelines, practices, evaluate your models, as well as services where we kind of take on and do labeling projects for different clients, both allowing them to really speed up their time to model, but also allowing us to get a much better understanding of any issues and problems that is possible to encounter when working with creating data sets for machine learning that we already had. So I kind of want to leave off there and welcome everyone in for some questions and answers in here. Let's see if I can open up that little Q&A here. One question coming in here for the ability to detect relations between different objects. And there, I assume this is for the OCR tool that I was showcasing just now. So kind of the way that was set up when I showcased relations that it automatically generated, kind of the address, the name. It's very useful if you have a predefined kind of data, so you know roughly what things are going to look like, and you can define what you want each row to be mapped to. But when it comes to detect relations between detected objects, that's an area of active research. I've seen that at Google, and kind of a conference around OCR is currently sponsoring what we call kind of hierarchical document recognition. That is exploring more ML methods for kind of automatically parsing entire documents, putting that information together. In the platform we have, it's possible to create manual relationships between different things, but the OCR tool doesn't automatically recognize all of them. Also had another question come in again, the Tesseract tool that we mentioned before, around if that still is using handcrafted features. And that is not the case. So Tesseract uses, it started out, HP developed it, and when it became open source as well, used kind of handcrafted features to both text the text in the scene and to parse the text as well, which of course made it a bit limited. It's hard to develop, keep track. If something changes your own data, it might change a large amount of thing about how you detect your data in here. But they've gradually made this framework. I mean, it's an open framework now. It's more than just an algorithm. It is a system, or like what they call an OCR engine. It's more motor or a vehicle where you can kind of plug and play with your sort of object detection algorithm and your text recognition algorithm. And this one runs the around things such as pre-processing, scaling your images, feeding output between these algorithms as well. So now that one incorporates more advanced neural networks as well. And the same goes for Paddle. Another question we have is about the use cases for OCR. When do you want to go for more of a pre-trained solution that is out there versus when do you have to train your own algorithms? And this, to a very large extent, depends a lot on your use case, right? If it's more document transcribing, there are very good solutions out there in many cases. But when we come in things like a dedicated or like relations between different objects mentioned before, complex document layouts that may be very specific to, say, your company or your use case, it might be necessary to create your own data set to adapt this. And then you can draw on existing algorithms and tools out there, but do small corrections, kind of transfer learning, or in some cases use what is known as an active learning approach. And it's kind of where you let the existing model guide you in your future labeling efforts. So a lot of models have the ability to themselves estimate confidence in their prediction, how accurate they are. And this can be used to, when the confidence is really low, you can have a look at that type of image, label it manually to use that and incorporate it into your data set, but also use some sort of image searches using embeddings to find similar examples to that you might also label and use to redo your relabel and add that to your data set as well. But this is mainly when you have more elaborate types of documents, or of course, if you're trying to transfer line or create something that can read, scripts that isn't available in these algorithms, or if you want to fine tune it on a use case, it can do, but really make it niche and increase performance there. It might also be a situation where it is necessary to train or create a non data set. From David, it seems like we have gotten a question also about kind of the difference between OCR and NLP. Did it go very close together. And the one needs the other in many cases, especially when you're working with like PDFs. And kind of leads into, for PDF specifically, I'm not sure how many of you have thought about how can you copy text from PDF? Because it's sort of an image, a vector-based image. Underlying there is actually OCR. Adobe started incorporating this into their PDF engines back in the 2000s. But having built-in OCR algorithms that kind of automatically transcribe the text segment you select, but also the entire document to change it into something you can edit. It's OCR that powers that. But that's a little bit of a sidetrack. So back into the original question about difference between OCR and NLP. Really closely, I would say that OCR is the reading part of understanding, and where natural language processing comes in is more understanding what you're reading or thinking about the text, in a sense. And that is something these large language models that I mentioned when we come into transformers are generally used for NLP, but they're more and more getting incorporated into powering OCR as well, where kind of preconceptions about how language is structured helps with also reading and understanding text. So more and more, to some extent, they're starting to blend into each other. I would still say that OCR is very much more focused on just reading the letter of the text, and the NLP is thinking, understanding it. And one more have pre-annotation. So when you're training an OCR algorithm, when you're using active learning, or when you're labeling in SuperAnnotate or any other tool for that reason, it might be very useful to have pre-annotated data. And that means that you have a model that you that can do some sort of machine learning task, some sort of NLP, some sort of OCR. It's really applicable to any type of machine learning, but for the OCR task, if you have something that can do OCR, you can run that on the data set that you currently have, and you can upload the results to a labeling platform such as SuperAnnotate to correct them and adjust them. And that is something that is very possible. Another question that we have down here is about the model that I showcased within the platform and its language capabilities. So OCR for every type of language can be tricky. Our model is focused specifically on, it can do Chinese characters, it can do Latin alphabet, it can do English and other type of Latin characters. For exactly which language support that is, I have to look up if we have a list of specifically supported languages. I'll get back to you. So there, I would like to say thank you all for coming. And if there's any questions that we haven't answered yet that you have sent in, we'll be coming back to you with them in a follow-up email. Thank you so much for coming and attending.